Hey folks, John here. Welcome to my series on deep learning. Over the next few weeks I'm going to be releasing videos where we explore deep learning and see how we can do some very powerful things with some of the frameworks and algorithms that are out there. The intent of the series is not to deep dive into the statistics or mathematics behind the algorithms that are going to be used, but really to showcase the power of the platform and how easy it is to potentially use some of that today in your applications or what you're building. I really want to kind of get you up to speed pretty quickly and then show you how you can start leveraging some of this cool stuff to do some very powerful things. Machine learning is all around us today, and it seems like it's being talked about at all times, but it's not a new concept. There's a video out there called The Thinking Machine, an MIT video, I believe, and this was back in the 1960s, and they were talking about intelligent machines and artificial intelligence. It's not a new concept. It's been around so long, we've had two winters called the AI winter. And these are basically a term for where AI had kind of gone into a lull and hadn't really taken off at that point. People were unsure if this wave of AI was also going to result in another AI winter, but at this point it seems to be becoming more and more ubiquitous, and it's something that we feel is going to drive things forward, and there's not going to be a winter at this point. We're kind of moving into the AI summer, I guess. We see it all around us in everything that we do. If I'm on Amazon, here's some recommendations for books. So if it's up to me, personalizing the experience for me based on things that I have bought in the past. We see Netflix doing similar things. If I'm looking at videos, it's going to show me things that it recommends for me. And this is based on my viewing behavior driven by machine learning under the hood. Why are we kind of now starting to see machine learning come to the fore, and why didn't it take off back in the 60s, 70s, or 80s? The biggest reason for that is the fact that we have cloud computing, we have computing at scale, and we have the ability to process large amounts of data and store that data and then leverage a large amount of computing power to train these algorithms on. And that's really changed the game from a machine learning perspective, because a lot of the machine learning algorithms that are used today work really well when you have more data to kind of train them on and more computing power to be able to train them on. And so by being able to leverage the cloud for some of that scale has really kind of moved the needle in terms of getting AI mainstream. We see it all around us in terms of things like translation, so using neural networks to do translation here. We've got Google Translate being very, very efficient at translating from different languages, being able to detect languages. We see hospitals using it to kind of do disease diagnostics to empower doctors to make better decisions on symptoms and helping drive that and reduce kind of misdiagnoses and things like that. The connected car is always being brought up. You have self-driving cars becoming more and more of a reality. If you talked about that, say, 15, 20 years ago, it would have been something you'd see science fiction writers write about, but they're a reality. They're on our roads today, and they're going to become more and more mainstream. Machine learning is driven in the devices that we have. If you've got like an Amazon Echo or Siri or Google Assistant, for example, those are kind of being driven by machine learning. They're kind of helping you do your everyday tasks and make your lives easier. So machine learning is all around us. It's helping personalize experiences, and it's helping drive behavior that makes our lives better. The military is also looking heavily at artificial intelligence and machine learning to improve their situation on the battlefield. And that kind of leads us to thinking about, well, I mean, AI can be used for a lot of good things, but we have to be cautious about it. Elon Musk is an advocate of kind of looking at caution around this. He says that we should be concerned about AI safety and about, will the machines end up being more powerful and need to be controlled? It's kind of that Skynet scenario, if you will. I mean, if we talk about some of the advances of machine learning, we have seen it come on leaps and bounds over the past few years. And ImageNet is a kind of collection of many, many thousands of images, and every year they're in a competition where essentially you can submit algorithms or ensembles of algorithms and try and train them against this set to be able to caption those images and identify objects in those images. And essentially, the intent of it is to be able to kind of identify what's in the image and see how that compares against other algorithms, and also how that compares against humans being able to identify objects in those images. And if we just look at this graph here, we can see back in 2012 it was doing okay, but it was, there was an error rate of about 16%. At this point in 2015, 2 years ago, the error rate was down to 3.5%, which was below the error rate expected for the human benchmark. So at this point, on this specific data set, machines were performing better than humans at recognizing objects and images. So they'd already kind of surpassed human expectations at that point. And so you can imagine, as computing power becomes cheaper and storage becomes bigger and cheaper as well, this is just only going to improve over time, and machines are going to be able to do things a lot more efficiently than we can in certain scenarios. So this series is called Deep Learning because we're going to focus a little bit more on neural networks throughout the series. In this video, I just want to kind of tee things up around kind of priming you at this base level what machine learning is. So we're not going to do neural networks in this video, but over the next few videos we're going to kind of deep dive into neural networks and kind of drill into what they are and how you can use them. Neural networks, the name implies they have some relation to the brain, and that's kind of a decent analogy here. So they're looking at a brain. You've got a brain which has neurons and synapses, and if you look at kind of what a neural network looks like at its basic core, you've got neurons and synapses between the neurons here, between the input, the hidden, and the output layers. So essentially, that's why it's called a neural network to some degree. It's kind of modeled in that sense. But we can take an input, drive it through some hidden layers, and then produce an output. This is a very simple neural network, and when you kind of get to the deep neural networks, these are just basically kind of that simple concept, just with many, many hidden layers to do more powerful training and learning on the data that you're passing in. Why are we looking at neural networks versus other ones? They're unreasonably effective. They do really powerful things, and they're certainly a game changer around machine learning. They're very, very resilient, and they're very, very useful across many different use cases, and we're seeing them being used more and more. A lot of the things that you see today that are being used by using machine learning are using neural networks to some extent to drive the behavior, and so we want to kind of focus on those because you can do some really cool things, and you can do those. It's becoming a lot easier to do those, and so I want to kind of spend time in that kind of category over the next few weeks. All right, let's talk about some of the base questions that machine learning can really help identify answers for. What about if we want to be able to identify whether an image contains a cat or not? I want to pass images in and it tells me this is a cat, this is not a cat. Here's an image, it's going to hopefully say this is a cat. Again, similarly here, we've got to identify this as a cat. This image is obviously not a cat, so hopefully it comes back and says, hey, this is not a cat. And when we think about this and break it down, we're really just basically passing in images, and machine learning algorithm hopefully will return whether it belongs to the cat category or to the not cat category. And really these could also be called classes, right? The cat class or the not cat class. And essentially this is a two-class classification problem. So this is a classification problem using machine learning to classify my objects that I'm passing in. And it's a very common use case that we see machine learning helping solve for. What about if we pass in an image like this, where, you know, maybe the machine learning algorithm hasn't been trained with a lot of data? How's that going to look? Be interesting to see. So then what if we want to expand that and say, what about instead of telling us if it's a cat or not, why don't you tell us the type of cat? So if you think about types of cat, there's many different types of cat, but each of those would be individual categories or individual classes. And so we train an algorithm across all of the classes of a cat that we want to be able to identify in terms of type. So we've got kind of Siamese cats, we've got Manx cats, we've got long-haired cats here. Sometimes we have grumpy cat, for example. So what categories would we want to kind of identify and have our cats bucketed up to? And then we train it on that. We have a labeled set of data, and that really allows the machine learning to kind of classify them. And this is a multi-class problem. So other scenarios where machine learning can come into play can be around being able to detect when there is some strange thing happening outside of the norms of most of the data that's coming in. A canonical example of this is credit card fraud. Doing transactions, I've got all this information about transactions users are doing, and then sometimes one or two fraudulent. So can we use machine learning to detect that? And we can. And we can use train the machine learning algorithms to look for things that don't look right in the data. So looking for strange things in the data. Another example, let's say I bought some stock and I want to be able to predict how well that stock's going to do in a few days' time, or tomorrow, or next week. And that's going to require us to kind of maybe potentially predict the price. So being able to say, hey, we've got all this historical data about prices and information about the company. Can we put all that into a model, train the model to then give me a prediction on what it thinks the price is going to be? And we can. Machine learning can be used to kind of quantify and predict kind of quantification of values and tell you how much something may be. So if your problem is around being able to kind of give you a quantifiable value, then potentially machine learning could be used to solve that as well. Another interesting use case, so if the past three use cases typically are kind of in that realm of supervised learning, where we've kind of provided a set of data which is labeled and has been labeled into the classes or the values that we want, and we trained it to kind of recognize all of the features to drive those labels. But sometimes we have data and we don't know if there's any patterns in the data, and we want to be able to identify patterns. So an example could be, let's say there's crime happening, and we've got all this crime information, but we don't know if any certain crimes are related, for example. Could we use machine learning to maybe look at all the data and the information about these crimes to give us groupings that machine learning thinks are related somehow? And maybe that can help us solve crimes going forward. And so this is another example of using machine learning, in this case, to do clustering or grouping within data sets. And finally, kind of another area of where machine learning comes into play to help solve is kind of determining next steps, right? So in this example, we've got self-driving cars driving along. They come to a stop sign and they need to turn right, turn left, go straight. They need to make decisions, and part of that is based on the context of things in the past and then what's going to happen in the future of where they're going, perhaps. So being able to kind of use machine learning to determine the next steps. Think about like this use case being applicable in robot vacuum cleaners, for example. Where in the room do they need to go next? Where have they cleaned? Things like that. Using machine learning to kind of predict the next steps that the algorithm needs to execute. So really, when we kind of think about it, machine learning can help solve problems where there's classification needed, where you're looking for something strange in the data, when you want to define or predict how much of something, looking for groups or clusters within data, also determining what to do next. So these are kind of 5 areas, if you think about it from a base perspective, to think about tailoring your questions that you're going to ask, or tailoring what you're looking for into one of these categories to kind of help choose the right algorithms you want to use, as well as also being able to kind of determine where the machine learning can actually help solve the problems you're looking to solve. All right, so let's walk through some of the core steps that all machine learning problems have to go through. So let's think about spam. Not this spam, right? So how do we use machine learning, or how would we go about creating a machine learning solution to detect for spam? And it's being used today. Machine learning is a good use candidate for kind of helping detect and filter out spam more efficiently. So where would we even begin to start? Well, let's think about what spam is, for example. So how would we, if we didn't have machine learning to learn about what spam is, how are you going to identify it? If let's say you were a programmer writing a program, you'd have to define a set of rules. This example shows different things you could look for. So you could write if statements, you could create rules to say, hey, if we see emails with caps, all caps in the subject with exclamation mark at the end, maybe if there's pricing and 50% off or discounting within the email, we can also flag that as spam if there's an attachment. There's a variety of things that if you look at spam emails, you can kind of generally see, but that continually changes. And so trying to maintain that set of programming rules and building that list gets harder and harder and harder as the spam folks keep changing what they're doing, being able to kind of bypass those. So what if instead of doing all of that complexity, what if we said, hey, let's give this list of spam emails and non-spam emails to an algorithm and let it learn to detect what spam is, looking for patterns across all of the data that we have. And really make it more efficient rather than having to write all these rules out. So the first step would be is gather a whole set of data. So as in all machine learning problems, you need data in order to be able to kind of derive things from it. So in this case, our data is going to be a set of emails, and the more emails we have, the better it is. And then really it's a classification problem, where if you remember before we talked about classifying cats or not cats, in this case it's classifying spam or not spam. And so we would have to go through, and it's a supervised learning problem, so we want to label our data set. So we'll label all of the emails that are spam as spam, and all of the ones that are not spam as not spam. So then we've got kind of a labeled data set that's got spam emails and not spam emails, and they've got a bunch of features about all of these emails, like who it's from, who it's to, all of that stuff, what the subject is, what the body is, etc. So we've got our data set and it's fully labeled. Next step is we'd want to split up that data set into a set of training data and test data. Training data typically is larger than the test data set, and we would want it to be split in such a way that we can kind of have enough data to be able to train the model, but also enough to test it and validate it. Now, the reason we do this split is because we'll use the training data to train the algorithm and get it to learn what this spam is, and then we'll use the test data as a set of data the algorithm has never seen before to then validate it. Otherwise, if we passed in data that we'd already used for training, it could skew the results and maybe pretend to appear to be more accurate than it really is. Then we've kind of got our data, we split it up into test and training, and then we'd want to choose an algorithm. There's a bunch of cheat sheets out there to kind of help identify algorithms based on the problems you're trying to solve. So this cheat sheet is one from Microsoft, and it kind of highlights those. If you start in the middle there, you can kind of define what are you trying to do. In our case, we're predicting categories. It's actually a 2-class problem. And so under there's a chart which for 2-class classification. There's several algorithms that can be used for 2-class classification. This is not an exhaustive list of all the algorithms out there. It's just a starting point to get you going. So we can look through here and say, hey, what algorithm have we used to help solve this? And is there always a right answer to this? And is it easy to know which algorithm to use? The answer is no. Sometimes it's trial and error, and typically for machine learning problems, you would choose maybe 2 or 3 different algorithms, try them out, and compare the results. At this point, you then train the model, and you go away and do some training, and depending on the size of the data, the type of algorithm you used, in terms of what you're trying to predict, for example, if it's 2-class versus multi-class, then how long is it going to take? And then basically you go through the cycle and it spends some time, and it could be minutes, hours, days, depending on what you're doing. But you're then training the algorithm. Then once you've trained it, you'll then pass in the test data and do some evaluation. You'll do some evaluation to try and see, hey, how good was this data set? And you can look at metrics like area under the curve, the score of the data, and really get an idea. And what you're looking to see is the predictions that are coming out better than a random guess, 50%, right? So if I throw a dart at spam or not spam, then is my machine learning algorithm performing any better than that would perform? And if it is, then you're onto something being useful to help solve problems. So that's kind of the final step, this evaluation, and then maybe you'll introduce other algorithms and compare their results to this and see if you can get better scoring. And so as we go through this set of series, we'll kind of talk about some of these aspects and how you kind of identify the performance of these different algorithms. But that in its essence is kind of the key steps. Get the data, make sure it's labeled and cleaned up properly. We'll then want to split it into test and training. We then choose an algorithm, we'll train the algorithm, and then we'll kind of test that algorithm and evaluate the results. So that at its core is the kind of key steps that we want to go through from a machine learning perspective for all of the machine learning problems that we face. Obviously, there's some nuances that we kind of glossed over here, but that at its core is kind of the process we'll follow for a lot of these problems that we use machine learning to solve. All right, let's try this out and see how it works on some data. So, and just to be clear, this is a deep learning series, but we're not going to use neural networks in this specific video because this is kind of a primer. The concepts you'll read about, you'll hear about here, are going to apply in the next set of videos where we will be using neural networks, but in this specific instance we're not, because we're kind of just laying the groundwork here. So, for this problem, just want to demonstrate some core machine learning concepts and how it works at its essence, and show you actually it's very straightforward. We've got a data set here, and this is a nice clean data set, so we're not going to do a lot of data manipulation, and they often say data manipulation is the hard part, so all of that's been taken care of. But we've got a set of data here that's got a bunch of properties about wine, and then we've got labels around the quality of those wines, from 0 to 10, with 0 being terrible and 10 being the best. And we want to be able to use this data set to train an algorithm to see if we can then predict wines given a set of these properties, such as how much alcohol, how many sulfates, things like that. Can we predict the quality of the wine based on that? So pull this data set from down here, and you can certainly go out to this site, it's uci.edu, pull this data set down and try it yourself. Alright, so as part of this I'm going to be using Jupyter Notebooks throughout this video series. They're easy to use. I'm using for now the hosted one sitting on Azure, so notebooks.azure.com, and you can go and check those out. It's a pretty easy way to start using them. First we're going to upload the CSV file, so we'll choose upload here and just upload the downloaded wine quality red CSV file here. So we'll choose that. So upload it here. Now we want to kind of import a couple of libraries to start leveraging some packages to use for this. So we're going to import pandas, we're going to import Seaborn here. Pandas for data manipulation, Seaborn for some visualizations. Now we want to kind of import that CSV. So just so you note, the separator on the CSV is actually a semicolon for this CSV. So we're importing that there. And then we're just going to take a look at the top 5 rows here. So you can see there's a whole bunch of columns. Quality is the one we're trying to predict. The others are kind of properties about the wine. If we look at the shape of it, we can see there's about 1,600 rows. There's 12 columns in it. So now we want to kind of import matplotlib to do some visualizations. We're doing a bit of data exploration here, so it's always good to kind of examine your data. Let's take a look at the quality label here. This is what we're going to be trying to predict. Let's see how well it's distributed in our data set. It's always important to kind of take a look at this, see if there's not any random skew that could throw things off, etc. So if all of your data was 10, for example, here, then it would be a problem. So here we're just going to use the matplotlib library to just plot a bar chart of quality counts and kind of see based on the buckets that the label has. So we're just going to kind of plot that out here, and we'll kind of see what that distribution looks like. So you can see there's a bunch of, in the middle there, between 5 and 6 quality wines. There's some 7, there's a couple 8, and a few 3. There's none really great at 9 or 10. There's none terrible at 1 or 2. Here's another useful thing to look at is correlation between the features, especially correlation between quality and certain features. So using the core function here, we can automatically create a matrix of those and kind of see how features are correlated with each other. It's really nice to use a Seaborn library to visualize this in a heat map, so you can quickly see which features are more correlated than others. So if we do that here, you'll see that actually with quality, for example, alcohol is quite well correlated. Sulfates seem reasonably well correlated with that. So there's definitely some correlation going there. So maybe those two features will help predict the wine quality. So now what we want to do is split the data into separation between features and labels. So here we just split that data set between X and Y, X being the features and Y being the labels here. So label being quality in this case. So we're just splitting that up into two variables called X and Y. Alright, so then we want to basically at this point leverage the scikit-learn library over here. A very powerful library. It's got a bunch of packages to make machine learning easy. It's got algorithms built in as well. So we're going to use some of those to make this easier, and I'd encourage you to check that library out as well. That's scikit-learn. Here we're using the train test split module, for example. It makes it easy to split your data between training and test. Here we're using 0.2 for test size, so 20% is test and 80% is training. I'm going to import the scikit-learn preprocessing library, and we're going to use this to do some scaling on the data. So if you look at the numbers from before, you'll notice that certain like volatility and sulfates, for example, could be wildly off in terms of how you'd compare them. So scaling allows us across a lot of data machine learning problems, allows us to scale the data so that it kind of is more aligned. And in using the standard scalar library of scikit-learn, we're basically giving it a mean of 0 and a standard deviation of 1 across the board. And so as you can see here, it's kind of created an NumPy array of that. So now at this point we want to look at bringing in an algorithm to use. So we're going to use logistic regression for our model here. We would have used a cheat sheet to kind of determine based on the problem. It's a classification one, what modules are available. Scikit-learn has a bunch of those, so logistic regression is the one we're using here. So at this point we kind of assign it to this variable, then we do fit on training data with our training labels, and then we'll kind of take a look at see how well it's performing. So at this point it kind of outputs a bunch, the model with a bunch of parameters and stuff that we could have tweaked, but we didn't. We just left the default ones here, so we've kind of fitted our data. Let's take a look at the confidence score of this. So it's about 57% here, not great. It's a little bit better than 50%, but not really too much more. So you know, we could certainly do some tweaking on our data and our algorithm perhaps. Let's take a look at how it does against the actual test data set that we put aside. Let's see how it does against data it's never seen before. So if we're comparing quality versus predicted quality here, we see sometimes it's doing okay, but sometimes it's also missing, and that's to be expected, especially given that 57% confidence score we have. So right now the intent here is to show you how easy it is to very quickly build a predictive model. We haven't had to write a lot of lines of code, so you know, you can see it's pretty easy to do. And hopefully you've been given throughout this series, or this video at least, a primer on what machine learning is. And next time we'll be kind of digging into neural networks and getting into some really cool stuff. So hopefully see you then. Bye.